Okay, great. Yeah, thank you for the opportunity to speak. Right, my talk is about chaos in thermal quantum systems, and here's the plan. I'm going to introduce the 4-point functions that we use to diagnose chaos using a simple spin chain as an example system. Then I'll discuss how to calculate these 4-point functions using holography, and then finally give an argument that bounds these 4-point functions that translates to a bound on the rate at which chaos develops in quantum mechanics. All this stuff is based on collaboration. The first two parts are based primarily on collaboration over the past couple years with Steve Schenker. I'll also draw on some work with Dan Roberts and Lenny Susskind. I'd like to point out that Alexei Kitaev has been working on related things. We heard a very nice talk from him last week, and I look forward to hearing more as the entanglement program develops. And Stefan Leichenauer, who's also here, has done some holographic calculations of this type. Okay, and the third part is based on a recent paper with Juan Maldacena and Steve Schenker. Okay, so to start, I'd like to imagine a thought experiment to illustrate the type of chaos I'm talking about, or that I will be talking about. Let's imagine that we have an equilibrium state in a thermal quantum system at time t equals 0. And let's act on that with some operator v, which creates some perturbation. Let's say a rather localized perturbation, which allows us to distinguish this state from the thermal equilibrium state. Now we evolve this system forwards in time to some later time. And what happens if the system thermalizes is the V perturbation sort of melds into the thermal bath. And we lose the ability to distinguish this state using this simple local measurement. Of course, if we evolve it backwards again, then the V perturbation emerges itself, reassembles itself out of the thermal bath, and we can identify that the state was perturbed in this way. But what if at this later time we perturb the state with some operator W, and only then evolve it back to t equals 0? In a sufficiently chaotic system, what happens, and if the time is sufficiently large, then what happens is this V perturbation fails to rematerialize. The W operator interferes with its rematerialization. This is a quantum mechanical definition of the butterfly effect. And this is the type of chaos that I'll be addressing in the talk. We can quantify this type of effect by looking at the commutator between the operator.
Do you want to say anything about how this compares to any other definitions of chaos that are out there for quantum mechanical systems?
Actually, no, I'm not going to do that.
Okay.
Are you going to clarify what qualifies as a thermal equilibrium state?
Yeah, so here it would be a state where expectation values of local operators are very close to the thermal expectation
But not necessarily an exact thermal density matrix.
No, not necessarily exactly thermal density matrix. As you know better than anybody, it doesn't have to be a thermal density matrix for that criterion.
I also know better than anybody that it's good to clarify these things at the beginning.
Okay. Okay, good. So this effect can be quantified by looking at the commutator between the operator v of 0 and w of t. What we're here saying is that the perturbation by w of t interfered with a possible measurement of v of 0. A useful measure of the strength of this operator is to take the thermal expectation value of its square, and with a minus sign here to make it positive. Here I'm assuming v and w are Hermitian operators. So to build some intuition for this commutator, I'm going to plot for you the result of a spin chain calculation of this commutator, where I take v to be a Pauli x operator at site 1, and take w to be, say, a Pauli z operator at site 5. Okay, the function is 0 at t equals 0. It's small for a while, and then it saturates near a value of 2. And I've been vague about the exact chaotic spin chain here because it doesn't matter. this is telling us something pretty interesting about the time evolution of this operator, W of t. So W of t, that's e to the iht, w e to the minus iht. Conjugation by the Hamiltonian makes this simple single-site operator into a more complicated operator. A naive guess that you might have had, okay, this is wrong, but let me just illustrate it. A naive guess that you might have had was that what we get here is some kind of sum over sites and Pauli indices of operators, spin operators, so that the spin z operator at site 5 evolves to a combination of spin x at site 1, spin z at site 10, and so on. If that were true, then, yeah, the commutator would be non-zero between the spin at site 1 and the later spin at site 5, but it would be small because the v operator would commute with most terms in this sum. That's not what's happening here. This commutator is becoming large, so this is not the right picture. Instead, the right picture is that this operator is becoming a sum of products of spin operators at various sites. As the time increases, the typical length of the term in the sum become longer and longer. And so in particular, for late time, the v operator at site 1 will fail to commute with most terms in this sum. That's how you get a large operator, how you get this commutator operator to be large. We can actually check this explicitly in these stupid spin systems by expanding this operator in a basis of products of Pauli operators. Okay, so here's another plot. Here's time. I'm going to plot for you the weight of this operator in Pauli strings of different lengths. So first of all, let's plot the weight in Pauli strings of length 1. Let's start.
What kind of Hamiltonian were you assuming?
Yeah, so this is a chaotic spin chain, a one-dimensional spin chain. I could write a Hamiltonian, but actually I won't. It doesn't matter too much.
But just sort of generic nearest neighbor interactions.
Yeah, let's say we have sigma x at site I and sigma x at site I plus 1. We also have sigma z, and we have a sigma x term.
People who do quantum chaos might distinguish between whether the eigenvalues of this Hamiltonian have Poisson statistics or Wigner-Dyson statistics.
Right. This would be the type of Hamiltonian for which the latter was true.
Okay, so you are in what would be called a chaotic regime.
Yeah. The type of Hamiltonian I'm illustrating here will satisfy any test that you have for quantum chaos, as far as I know. Okay, good. So here's the weight of the Pauli strings of length 1 as a function of time. It starts out large, and it decreases. Here's the weight in Pauli strings of length 2, and length 3, 4, and so on. So as time increases, the operator gets more and more weight in longer Pauli strings. That's what I was illustrating here. This data here is due to Dan Roberts, who's informed a lot of my understanding of chaos in these spin chain systems and more generally. So, yeah. Mm-hmm.
Just to confirm, this is translational invariant?
Is what translation invariant?
The Hamiltonian.
Yeah. The Hamiltonian is time independent. Oh, sorry. Yeah, yes.
And in space?
Yes, yeah. For the specific examples we considered, yes.
And this is just exact diagonalization.
Right. So here, we're very humble. We were doing 10 spins or something. Yeah. Yes.
Go ahead.
If these are separated by distance x, these operators, v and w, the time at which you see is the, if you try to extract the velocity at which it picks up, is it exactly same as what people would call Lieb-Robinson velocity in terms of, or is it different?
Well, so this could actually be a calculation of the Lieb-Robinson velocity. And normally, the Lieb-Robinson velocity.
As the user,
so there, the Lieb-Robinson bound has some coefficients,
right,
which are some sort of sloppy bounds on terms in the Hamiltonian. But this, I guess, would be, this would be a calculation of that. There was another question. Yeah, Veronica.
Just to clarify what you have just sketched, so
yes.
it's sort of out of all, say, operators of length 5, you sort of average over them, and then you get this plot, or it's some typical one?
No, good. So here I was taking a very specific operator, which was sigma x at site 5. I was evolving it for some time t, and then expanding it in sums of products of Pauli matrices. Mm-hmm. And what was being plotted here was the sum of the squares of those coefficients in the expansion for fixed Pauli length.
I see. Okay, good.
Okay, so
Excuse me.
yes.
Do you consider the high temperature case where this sum of the squares of the coefficients is conserved, or?
Yeah, so the sum of the squares of the coefficients is exactly conserved.
Conserved when it's the infinite temperature state. Otherwise
Here we're not talking about the state, just the evolution of the operator.
Oh, yeah.
For that,
sorry.
the sums of the squares are exactly
Yeah.
conserved.
I mean, the sum of the squares of the coefficient is the expectation value of the separator on the maximally mixed state.
Yeah, so that's true at high temperature. But this doesn't depend on the temperature.
Yeah, I understand.
Okay, so as a criterion for chaos, we'll use the idea that this commutator should become large independently of the choice of V and W operators we have, as long as T is large. And it's helpful to unpack this definition a little bit by writing out the four terms here. We have a term which is V W of T V, plus a term W of T V W of T, and then minus a term V W of T V W of T, minus W of T V W of T V. Okay.
And is the idea that this is largely state independent, or is there a particular?
Right. So here I'm imagining that we're doing the calculation in a thermal state. But it should be independent of precisely what thermal state we choose. It will depend on the temperature, but it won't depend on the precise microstate. Okay. So at large time, what we have, the terms on the first line actually approach order 1 values. The way to understand that is, by order 1, I mean they become of order WW times VV. Way to understand that is to think about this as a 2-point function, as an expectation value of the operator W squared in a state where we perturb the thermal state by the operator V. Especially if the time separation is large, then that will reduce to the 2-point function of W in the thermal state multiplied by the norm of this state, V acting on the thermal state. That's not true for the terms in the second line. Here, it's not an expectation value in the state. It's an inner product of a state where we've applied first W and then V, with a state where we first applied V and then W. If the difference in time between the operators is large, these states are orthogonal, and these expectation values in the second line are small. This is why the commutator becomes large. This is a second and more convenient criterion for chaos, that the 4-point functions with the ordering WV, WV should become small at late time, regardless of the choice of V and W operators. Okay, so I'm finished with section 1. Now I'm going to begin.
Douglas, when you say regardless of the choice, you want them to be local on the spin chain, or is that?
I think it's not necessary that they should be local on the spin chain. So you could make a stupid choice, like you could take the Hamiltonian. And it won't be true for that operator.
I mean, there are other things that are, different weights of projections on the eigenstates.
Good. So I want these operators to be simple in the sense that they are composed out of products of order 1 of the degrees of freedom. Now, I might allow it to be a sum of such operators at different sites, and I could get into trouble because you could build the Hamiltonian out of that, but as long as you don't choose the Hamiltonian, it should be true.
Or square of the Hamiltonian.
If you'd like, we can just say local and composed out of order 1, products of order 1 degrees of freedom, and then that problem doesn't arise. Okay, good. So now let's illustrate how to calculate these things holographically. The idea is to split up this 4-point function to think about it as an inner product of 2 states, where we have a ket vector here and a bra vector here. We'll understand how to represent these states in the bulk, and then we'll take their inner product in the bulk. So how can we do that? Well, first of all, this thermal state here is represented in holography by an ADS black hole, if the temperature is sufficiently high. And at this point, I'm going to consider a specific thermal state, which is the thermal field double state, in order to make the pictures I draw a little simpler. Although here I'm talking about, quote, one-sided observables, which won't depend very much on that choice. But, so let me draw here the thermal state beta is this ADS Schwarzschild geometry. And we need to understand what the bulk states look like when we apply products of operators W of t and V. Actually, to make the notation slightly, well, to make the picture slightly clearer, I'm going to think about an operator W at time t over 2, an operator V at time minus t over 2, instead of 1 at t and 1 at 0. So to warm up, let's understand what it looks like if we act with the operator W at time 0 on this state. Okay? So we start with the black hole, and we make a perturbation at this time. We're going to assume also that this operator is roughly thermal scale, that its energy that it raises the energy by an amount of order the temperature. This creates a quantum, or several quanta in the bulk, somewhere outside the horizon. It creates a wave function for a quantum somewhere in this region. If we follow the evolution of this quantum forward in time, it falls through the future horizon. If we follow it backwards in time, it falls through the past horizon. I'm drawing here a classical trajectory, but really the correct description of this would be a wave function for the quantum sourced by this W operator.
Is this operator unitary?
No, so it's not unitary. We could consider unitary operators, but that's not necessary.
So then it can do a little bit of stuff to the left.
Yeah, yes. So there's a wave function, right? There's a wave function on this slice for the particle. And, it will have some weight. Most of the amplitude will be somewhere out here. Okay. Good. So now let's understand how to create this state where we have W at t over 2. We can get that from this geometry simply by applying a time translation. This point moves up here. The trajectory that I drew becomes that trajectory. The important point is that if we look at this state on this t equals 0 slice, then the quantum here will be highly boosted. It's a fact familiar to experts, and a fact that I guess I won't explain if you don't know it already. You'll just have to take this on faith. The time translation of the boundary corresponds to a Lorentz boost of the near horizon region. The boost parameter e to the 2 pi over beta times delta t. So if the original quantum had energy of order 1 on this slice, then in this state we have a quantum with p plus, that's the momentum in this direction, of order order 1 temperature scale times e to the 2 pi over beta t over 2. If we were to write this state instead, it would look very similar, except the trajectory would be like this, and we would have p minus of order t e to the 2 pi over beta t over 2. Okay, so how do we put these together? First, we act with this operator and then with V. It's simplest to do this if we think about the state on this slice which touches the boundary at time minus t over 2. Here we have a state with a W quantum here, highly boosted. We add to that this V quantum, which is highly boosted in that direction. So the state V of minus t over 2, W of t over 2, looks like this. We have a W quantum and a V quantum, and they're highly boosted with respect to each other. The center of mass energy, P plus, P minus, is of order T squared times e to the 2 pi over beta times T.
So you're assuming something about the map here that, acting with your W operator on the boundary is giving you, something like a localized quantum in the bulk. So
How localized it is isn't terribly important. What was important here was that it created some quantum with some wave function with order 1 energies. I've now boosted it by a large amount, and Lorentz contraction is going to make it very close to this.
But, well, okay, so the wave function that you started with doesn't matter.
It doesn't matter, right?
If some wave function.
Some wave function. Right. Yeah, yes. Thank you for that question. Good. If you followed through the this construction for this state with the opposite ordering, you would have found a very similar picture, but now we would have had these quanta up here. So here's the W quantum in both cases, and here's the V quantum. So this ket vector corresponds to an in state in the scattering problem, and the bra vector corresponds to an out state. That's what the difference in the ordering of these operators does. This means that their overlap here, this 4-point function, is a bulk scattering amplitude weighted against wave functions for these quanta. It's very convenient to use, good. It's a bulk scattering amplitude in a particular kinematical region where we have large S, but impact parameters which are fixed by the separation of V and W operators on the boundary. So it's a Reggie type of kinematics where we have fixed impact parameter and large S.
There you're assuming that you have some kind of wave function, specific wave function in the bulk property, right?
No.
What's localizing in the sort of trend space?
I didn't say it was particularly localized. Although it's actually true that it will localize over scales of order beta, because the propagation from this local operator to the bulk boundary propagator is suppressed on scales transverse separations larger than beta.
You should say that the transverse momentum is not growing as scale.
Yeah, that's the important point. Okay.
Well, yeah, it's one.
So for this type of scattering, it's very useful to use a basis where we have longitudinal momentum and transverse position. So this would be a ket vector for the W quantum with large P plus. This would be a ket vector for the V quantum with large P minus. And in states are related to out states by multiplication by this iconal phase, which I'll define in a moment, Q plus X, Q minus Y out, plus a possible inelastic contribution, which is orthogonal to these two particle states. So the statement is that in this kinematics, the S matrix is diagonal apart. Well, the 2-to-2 part of the S matrix is diagonal in this basis of longitudinal momentum and transverse position. And the S matrix element is this complex number, e to the I delta of S and B. Just parameterizing the complex number by e to the I delta of S and B, where S is P plus, Q minus, and B is X minus Y. Yes, Gary?
Yeah, I just realized I'm a little confused. So you're acting with operators on the boundary at these times, but then drawing the bulk as if the excitation always existed.
Right.
In the past.
Yeah. This is a slightly confusing point. It's not, the point is not that we're starting from a particular state and then acting, changing the Hamiltonian to introduce some perturbation. What we're doing is we're representing states with a time-independent Hamiltonian. And so this state here is a state where there was a particle that emerged from the black hole horizon, approached the boundary, and then fell back in. The Hamiltonian is strictly time-independent here. And this, forget about the fact that there's a time argument associated to this operator. Just think about this as a state vector. The bulk picture is this. Tom, you had a question?
Yeah, so you're thinking of the scattering now as taking place, roughly speaking, in Minkowski space?
Well, yes and no. It's happening very close in the coordinates represented by this diagram to this point, but the transverse separations might be large compared to the ADS scale. The separations along the horizon might be large compared to the ADS scale.
I see.
Okay. So what goes here, good, this is a good point, good time to make this point. What goes here is not the flat space iconal phase. what goes there is an iconal phase that we calculate using shock waves on the ADS Schwarzschild geometry, following the analysis due to a 't Hooft for flat space. And the result in general is this phase is suppressed by g Newton, but it's proportional to s, and it's a function of b, where this function is exponentially decaying with transverse separation along the black hole horizon. At very high energies, this phase, this isn't accurate, and the phase becomes complex, reflecting the fact that some of the state vector is going into inelastic final states. Okay, so good. So we can use this now to write a formula for this 4-point function. No, not that 4-point function. This 4-point function. And the formula is as follows. We integrate with this phase factor. I'll just write the expression and I'll explain it. So we have this S matrix element times the product of wave functions. The wave functions 1 and 3 are the wave functions for the W quantum. This is 1, 2, 3, 1, 2, 3, 4. And what we have, these wave functions are Fourier transforms of the bulk to boundary propagators from these points. The factors of P plus and Q minus are here for the Klein-Gordon inner product of these wave functions. A formula very similar to this was independently derived by Kitaev. Both of us were using this analysis of a 't Hooft in the early 90s, I think. So let's imagine for the moment that we remove this factor, set this equal to 1. Then what we have here is two decoupled integrals, sets of integrals. This one gives us the WW 2-point function, this factor, and this factor gives us the VV 2-point function. So at very small g Newton, we just get the product of VV, WW. But as we increase T, the typical value of the center of mass energy increases exponentially, and this phase starts to oscillate and suppress the 4-point function. And the type of dependence that we get is something like this. The function is approximately equal to VV WW for a rather long time, because g Newton is small. Then eventually it starts to decrease.
And how flat is that flat region?
I will address that in a moment. So let's imagine now, good. I should mention the behavior of the function in this large T region depends on the specific choice of V and W operators, because what you end up looking at are the tails of these wave functions where the center of mass energy is not too high. But in this region here, this is a region where we almost have just the product of 2-point functions. That's because this phase is close to 1. We can estimate the behavior of the 4-point function in this region by expanding out that exponential. What we have is the expectation value with all these wave functions of 1 plus I g Newton s f of b plus order g Newton squared. Okay. So I told you that the typical value of s in these wave functions is of order e to the 2 pi over beta times t. So what we get here is the expectation value of 1, which would be the product of the 2-point functions, plus I times g Newton, e to the 2 pi over beta times t, times this function evaluated at the difference between the transverse location of w and v.
There's something I'm confused about. If you go to long enough time, you go to very, very high energy, and you're going to probably go out of the iconal region and be doing something like making big black holes or whatever, getting into the strong gravity region. And is that's part of what you said with regard to the inelastic? Okay, so why don't you're working at times that are short enough I don't have to worry about
Not necessarily. In making this expansion, yes. But you can analyze this function. Yeah, so initially Steve and I were excited by the possibility that, black hole collisions and interesting features of the high energy S matrix might be visible in this 4-point function. It turns out that that's basically not true. And the reason is that this integral is dominated by tail at very late time, so that naively the center of mass energy is extremely high. This integral is actually dominated by tails of the wave functions where the phase is of order 1. So the important physics for calculating this 4-point function is actually the gravitational scattering where the phase is of order 1.
So it's sort of the part that misses being the black hole.
Right, so you're not making black holes in that region.
Yes, the long range.
You just have this very,
yeah, you start to see
this is the traditional
gravitational field, but
yeah. Okay, so good.
Excuse me.
Yes.
You wrote this exponent as delta of s comma t. Isn't it just s times some function of b?
Right. That's what this is. So I put in here the answer in gravity.
In gravity.
I'll discuss a little bit the behavior of this thing in string theory, where it's not exactly decoupled between s and b.
Thank you.
Okay. So good. So what we have here, let me translate this into field theory language by replacing g Newton by 1 over n squared. Okay. So we have a function that's very close to 1. This is now answering Don's question. This is a function that is very close to 1 until this time is of order log n squared. So the correction to 1 here is 1 over n squared times something that's exponentially growing. Okay, you might be puzzled because this thing looks like the magnitude should be growing with time. This is 1 plus I times something, whereas what I've drawn here is something that decreases. And the point is that actually at linear order, the magnitude of this function does not change. You have to go to second order to see a change in the magnitude. A good model for this function would be 1 plus I over n squared e to the 2 pi over beta times t raised to some power. This has such an expansion, but at large t, but in fact the magnitude of this function is monotonically decreasing, and at large time it's really small. Right, so good. So as I mentioned, the late time behavior of this thing is not universal. It depends on the specific choice of W and V operators. That'd be like this power here depends on W and V, but the rate of exponential growth does not. The rate of exponential growth, yes, Sasha?
Do I understand correctly that if you just keep generic delta, then the formula will be like 1 minus I delta S and B, where you evaluate S to be exponent and B to be separation. So
right.
That's what.
Yes. Good. So the rate of growth of this term is universal. It doesn't depend on the particular choice of W and V operators. And this exponential here defines something that Kitaev has referred to as a Lyapunov exponent, and I'll use that notation. We define this 2 pi over beta to be the Lyapunov exponent lambda L. It controls the rate of growth of the exponential correction to this.
I'm confused. You said that your function is really monotonically decreasing over this entire almost flat region?
Mm-hmm.
Maybe I got the sign wrong, but I would have thought that, I mean, I understand that there's your something small multiplied by exponential growth, which is the signature of chaos. But in the gravitational context, I would have thought that before that started, you should see a region where there's quasi-normal ringing and you get a decay of the commutator. You know, if you had phi with the same field at a later time, you see the commutator decay for some time before it starts to grow again. Does that not happen?
So, good. That can happen if the V and W operators have a non-zero two-point function in the thermal state.
Yes.
So here, in this analysis, I'm assuming that they have a zero two-point function in the thermal state.
Great. Okay.
One can understand the case where they don't, where that's not true, but I'm ignoring it.
Is it just a question of the two-point function? I would have thought that, again, if I had two scalar fields of different flavor that interacted slightly, you know, through some gravitational exchange, that maybe the two-point function would vanish, but there'd be some non-zero 3- or 4-point function, and I would still see a similar...
No, so actually, I think you should hold this comment for the third part of the talk, where the fact that this function is bounded by its initial value is what allows us to derive a constraint on this. Okay, so we define this Lyapunov exponent as 2 pi over beta. And the time until this correlation function starts to deviate significantly from 1, so the time I'll denote as t star. So that would be here, beta over 2 pi times log of n squared. Going back to the spin chain example, what's happening here is the time t star is the time at which operators involving, let's say, one of the matrix degrees of freedom have evolved to become products, or rather a sum of products, where each term in that sum involves a product of order n squared degrees of freedom. More generally, at time t, it involves products of length e to the 2 pi over beta times t. So the commutator is of order e to the 2 pi over beta times t divided by n squared. This time scale has shown up before. 1 over the temperature times the logarithm of n squared is a time scale that's referred to as the scrambling time. And it was proposed by Hayden, Preskill, Sakino, and Susskind that black holes are very efficient scramblers. Sakino and Susskind proposed that they were the fastest scramblers allowed by quantum mechanics. So it's interesting to consider the conjecture in this case that not only this logarithmic behavior is special, but the numerical coefficient here is actually as small as it is possible to, as small as is allowed by quantum mechanics. That is, the exponential growth here of this first correction to 1 can never be faster than e to the 2 pi over beta times t. That's the subject of the third part of the talk. Right. Yeah. I should mention that that's sort of also in the spirit of this viscosity to entropy conjecture of Kovton, Son, and Starinets, who, again, were sort of working with the intuition that black holes are somehow dual to quantum systems that are interacting as strongly as is allowed by quantum mechanics. So as I said, we'll get to that in part 3. But before I start that, it's interesting to consider how robust this conclusion would be, this 2 pi over beta would be, to changes in the bulk theory. So, yes, Edgar?
As far as if you're below the Hawking page temperature, doesn't octanol calculations change?
Right, so if you're below the Hawking page temperature, then there's no black hole, there's none of these boosts, and the commutator does not become large. Yes?
Can you say again what does n correspond to in the spin chain? Is it just the length of the spin chain?
Well, so here, no. So the spin chain doesn't really have a parameter like n. N would be like the number of degrees of freedom at a single site. So in the spin chain, n is 2 or 1 or whatever.
As a technical point, based on what you said about the Hawking page phase transition, did you really need that this be a thermal state, or could you basically work in a typical state in the microcanonical ensemble and claim that it's valid quite a bit below what's actually Hawking page?
That's a good point. Yeah, you could do that should be true. Right.
And the growth in the spin chain, the initial growth is again exponential? Is that?
This is something I actually don't know the answer to. So the Lieb-Robinson bound is exponential, but I'm not sure whether the actual behavior is exponential. That's something that I would like to know more about.
So you're saying we know that it's slower than exponential? Is that?
And we don't know that it's slower than exponential. The bound is exponential. Okay. So we can consider a few different modifications to this calculation in the bulk. A simple modification we could make is we could consider different W and V operators. I've sort of already discussed this. It doesn't matter. The reason it doesn't matter is that everything couples to gravity, and the time dependence here was just determined by the rate of growth of the gravitational interaction. A slightly less trivial variation is to consider higher derivative corrections to the Einstein action. In the context of this viscosity to entropy bound, this was a problem, right? By adding higher derivative corrections, you can violate the proposed bound. But here, nothing changes because the high energy scattering, even in a higher derivative theory of gravity, is the phase is always proportional to S. This S here is really S to the J minus 1, where J is the spin of the exchanged particle. And higher derivative interactions don't change the spin of the graviton.
Just saying that's the leading long-range contribution.
Yeah. Well, yeah. Well, the detailed form of the gravitational interaction could be different, but the growth with energy will be S. Good. So a slightly less trivial example is to consider stringy corrections in the bulk. And following work by Brouwer, Polchinski, Strassler, and Tan, Steve and I calculated the first alpha prime correction to this scattering in the black hole background. And what one finds there is this exponent S to the first power is corrected to S to the 1 minus some constant times L string squared divided by L ADS squared, where this constant depends on the particular black hole. But one can show that it's always positive. In other words, this amplitude is always growing less rapidly than in gravity. That means that the string-corrected Lyapunov exponent would be 2 pi over beta times 1 minus this constant times L string squared all over L ADS squared plus higher order in the alpha prime expansion. This all provides some sort of circumstantial evidence that there should actually be a bound on the rate of growth of this term. Another stronger piece of evidence comes from this work by Kamanho, Edelstein, Maldacena, and Zhibudov, who argued in the context of a model, a signal transmission model of high energy scattering, that unitarity, causality, and analyticity implied that the tree-level answer can't grow faster than S to the first power. Okay. So this all motivates the conjecture that this growth we found in gravity of this first non-trivial term is actually the fastest that's allowed by quantum mechanics. And that will be the topic, presenting a mathematical argument for that will be the topic for the third part of this talk. Yes, Guilherme?
Is the coefficient C order 1?
Is the coefficient? Yeah, so yes. So for high temperature ADS black hole, this coefficient is some function of the space-time dimension. It's order 1. Okay. So in our paper, Juan and Steve and I try to make a rather general argument. And for the purpose of this talk, I'm going to make a slightly less general argument. I'm going to focus on the case of a large N quantum mechanical system where the V and W operators have 0 thermal 2-point function. Also going to assume that the V and W operators have 0 thermal 1-point functions. And the way we're going to attack this problem is to consider this 4-point function, f of t, which is a thermal trace of y. I'll define y in a moment, times this sequence of operators where y is equal to the thermal density matrix to the 1/4 power. Okay, so this is like a thermal expectation value, but I've sort of split up the density matrix into 4 pieces that are sitting between these operators. You can write a contour for this thing. So this is the thermal circle. Then we've inserted a V operator here, a V operator there, and then a Lorentzian fold to produce the W of T operator, and another Lorentzian fold down here. So the contour ordering is V, W, V, W, and there's 1/4 of a Euclidean circle between the insertions. That's these factors of Y.
Sorry, can you explain why are we splitting this? What is the motivation?
Yeah, so that will become clear as I proceed. This function has some nice properties. But first, let me just mention that you can use holography to calculate this function the same way that we calculated this 4-point function a moment ago. And what one finds is f of t is equal to fd, a constant which I'll define in a moment, minus, now there's no factor of I, minus 1 over n squared, some constant, e to the 2 pi over beta times t, plus order 1 over n to the 4th. Okay?
How do you use holography to calculate something that involves rho to the 1/4?
Well, so here, what this corresponds to is putting complex times for these operators. All that affects are the wave functions. So we have bulk-to-boundary propagators, and the boundary points are no longer just on the at real time; they're at complex time. The scattering analysis is the same. Okay. So. Good. FD here is equal to the disconnected contribution of the 4-point function, which in this case, where there are no VW 2-point functions, is trace y squared V times trace y squared W, y squared W. Our conjecture, a sharp version of this conjecture for about the Lyapunov exponent is the following, that the time derivative of fd minus f of t should be less than or equal to 2 pi over beta times the same difference. So if we plug in this form here with a general lambda instead of the 2 pi over beta, we would find the constraint that lambda should be less than or equal to 2 pi over beta. So this is the sharp mathematical conjecture that we'll now provide a mathematical argument for.
Sorry, at what times? At any time?
Yeah, good. So in the setting that I'm discussing now, where there are no thermal 2-point functions between V and W, then yes, at any time. At any time before, let's say, Poincare recurrences. Well, yeah, let me say that. For the more general case, what you have to do is you have to wait to apply this equation a little bit until the off-diagonal 2-point functions between the V and the W operators have become small. At that point, we can apply the same argument that I'll present here. That's a technical remark. Okay, so the strategy here is to list some nice properties about this function and then see what we can do to prove this statement mathematically. So one property is that f of t is real. This follows from the fact that the V and W operators are Hermitian. A second property is that f of t plus I tau is analytic in a strip in the complex plane of width. I'll only care about positive time of width beta over 2. So here's a strip. Here's I beta over 4 minus I beta over 4. This function defines, this formula here defines an analytic function in this strip. Way to see that is to just put in t plus I tau here, what we find is f of t plus I tau is equal to the trace of y to the 1 minus 4 tau over beta. It could be that this is plus. I hope I haven't got this backwards, but I easily could have. Y1 plus 4 tau over beta w of t minus 4 tau over beta. Okay. And if the magnitude of tau is less than beta, beta over 4, then this is an analytic function. Good. So there's a mathematical fact which follows from the Schwarz-Pick theorem in complex analysis, which is that if a function which is real on the real axis and is analytic in this strip satisfies an additional property that f of t plus I tau everywhere in that strip is less than or equal to fd, then this statement follows. Or more precisely, this statement follows up to a term which we have to correct 2 pi over beta by, which is exponentially decreasing in time and is unimportant after t is greater than beta, or twice beta. So really all we have to show is that this inequality is true everywhere in the strip. Yeah, this Schwarz-Pick theorem follows from a bound on the derivative of a function that maps the unit disk into the unit disk. Okay, we can we can chain together another result from complex analysis and say that in order to show that this is true everywhere on the strip, all we have to do is show that it's true on the boundaries of the strip. And then we can use the maximum modulus principle for complex functions on strips, which is called the Fragment-Lindelof principle, to conclude that the function is actually bounded by f of d in magnitude everywhere in the interior of the strip. Okay. So, good. There was one other thing I wanted to mention about this, but nobody has asked me about it, so I guess I won't.
Just a small question. If I move these y's around, are there some similar?
Move the y's around?
Yeah, I mean, I don't put them. You did them in a staggered way, like you define y, vy, then dy. Constant sound. I mean,
well, this is sort of moving the y's around.
This one.
So you can do this. But it's important for the argument that as we make this continuation, everywhere in this strip, the v operators are antipodal and the w operators are antipodal around the thermal circle. Yes?
Can you please explain the connection with your previous scattering experiment? So
The connection between what? And
between f of t, which is real, and the computation which involves high energy scattering, which has...
It's a high energy scattering amplitude, but with wave functions, but with different wave functions. With wave functions that are bulk to boundary propagators from points with Euclidean time on the boundary. So if you're able to compute these bulk wave functions, as you can, for example, in ADS Rindler, you plug in those wave functions, you put in the usual scattering amplitude, and then you do the integral. And the integral, it's no longer... The integral is no longer, the first correction is no longer imaginary, it's actually purely real.
So can you write f of t as a, if I give you delta of s and b, which is a scattering phase, can you write f of t in terms of this phase? Or?
Yeah, I think the f of t for real t,
yeah.
I think it's related to the scattering amplitude at purely imaginary s. So the first correction is related to delta at purely imaginary s.
Because then imagine you have a string theory and you have s to some power p. And if s is 1, and then I have an imaginary s to some power p, why would it be real?
It actually is true that it's real at purely imaginary s.
It's real.
Yeah, this is true. there's this phase factor, right? So the thing you're worried about is that you have s to a fractional power, but you also have a complex number multiplying the amplitude.
Yes.
And this whole thing is actually just, it's like minus I s to a fractional power. So if you put in s as purely imaginary, then you get a real answer.
Question.
Yes?
So in other contexts, we know that, for example, entanglement entropy, you can have phase transitions. How do we know that, how confident are we about the analyticity of this function? How do we know there isn't a phase transition?
We're completely confident about the analyticity because this defines an analytic function.
You could say the same thing about trace flow to the end.
Well, apparently not, no.
How do we know?
So here, the reason this function is analytic, it's the same reason that Euclidean correlation functions are analytic, even with point-like operators.
It's asking, so here it's analytic for finite n, but it's asking why infinite n there couldn't be a phase transition.
Can there be a subtle limit?
At infinite n, I don't think I have anything particularly insightful to give you here. But at finite n, it's analytic, and we're calculating the, well, yeah. I guess at infinite n, this function is just equal to the disconnected answer.
I guess it depends on how much time you evolve.
Well, but for finite time and infinite n, it will be just a disconnected answer.
But the transition also happens at an infinite t
Right.
in that case. But I want to consider whether it's analytic.
You want to consider both infinite t and infinite n.
Well, this is a limit that you want to take.
We want to consider large n
Yeah.
and large t, but and as finite, the function is analytic. Okay, good. So how do we argue that this property is true on these three boundaries? The argument on these two boundaries is identical, so really we just have two boundaries to make the argument on. And this is where the argument I'm going to present in this talk is a little bit simpler than the argument that Juan and Steve and I presented in our paper. I'm going to use large N factorization to simplify the analysis. So this function at on general grounds, this function should be given by f of t should be given by the sum of the disconnected two-point functions plus something that's order 1 over n squared. So in the case where the v and w operators have no thermal two-point function, this is f of t is equal to f of d plus order 1 over n squared. Now it's important here that the order 1 over n squared term is growing with time. That's sort of the whole point of this analysis, is that this is exponentially growing with time. And so you're not, in general, allowed to ignore this term. However, if we look at the edge of this strip here at small time, what I've drawn here at time t equals 0, then this will be order 1 over n squared without any enhancement due to large t. So it will really be a correction which is of order 1 over n squared. So everywhere along this boundary, we have that f is equal to f of d plus some small correction. So this inequality holds on that boundary up to a error which is of size 1 over n squared. That's the easy boundary. The horizontal boundaries are slightly more complicated. So it's helpful here to write out f of t minus, let me consider the lower boundary, f of t minus I times beta over 4. That's equal to the trace of y squared v w of t, y squared v w of t. I'm just using this formula here. Have I got it right? Yes. Okay. We can regard this thing as the inner product of two vectors, quote vectors, where the vectors are y, v, w of t, y. This matrix ij, I consider the I and j indices as one vector index. The inner product of this vector with a vector the complex inner product of this vector with the vector y w of t v y, again with ij indices. That is, it's this vector multiplied by the complex conjugate of this vector and summed over the index. The Cauchy-Schwarz inequality then implies that this in magnitude is less than or equal to the product, the square root of the product of the norms of these vectors. Okay? It turns out that these norms are equal to each other, and they're given by trace of y squared v w of t times y squared w of t v. Okay, now, so this is an inequality that holds on the top and the bottom edges of this strip. And again, it's true that this 4-point function, by large N factorization, should be given by this disconnected piece plus something that's order 1 over n squared. But the crucial point is that for this ordering of the 4-point function, we do not expect the order 1 over n squared piece to be growing with time. This is an assumption that we're making, but I hope the following picture will make this seem like a very reasonable assumption. The contour that we have to evaluate this 4-point function is the following. We have half the thermal circle, then we have some Lorentzian time t, the other half, and we've inserted w here, w there, v here, and v there. That's to be distinguished from the contour where we have this, a w, a v here, a w, and then a v here, and then a w. So these are quite different. In this case, factorization does not hold at large time. Instead, this 4-point function becomes small. But in this case, large time should only make the factorization better, because the w operators are close to each other, the v operators are close to each other along the contour, but they're getting farther apart from each other. So this factorization, where we replace this by fd, that is trace y squared w times trace y squared v, that approximation should only get better at large t. So we conclude that this is less than or equal to fd plus order 1 over n squared uniformly in time. That we can bound this thing by the disconnected answer plus a uniformly small correction. Okay, so that finishes the argument. Now we've bounded the function on this strip, on this edge, on that edge, and the argument for this edge is identical. I realize I'm drawing on something invisible, but you guys have good memories anyhow. So, right, so the conclusion is that this holds up to errors that are of order 1 over n squared and uniform in time. We can conclude from that this Schwarz-Pick inequality holds d dt, fd minus f of t less than or equal to 2 pi over beta, fd minus f of t, plus, again, a uniform 1 over n squared correction. So now if we imagine that we put in, right, so this is the result. We could imagine now that we put in an ansatz here just to illustrate how unimportant this correction term is. 1 over e to the lambda t times 1 over n squared. So the time derivative of this thing less than 2 pi over beta times that same function. The point is that this term on the right-hand side is growing exponentially with time. This one is not. So as long as time, as soon as t is a little times 1 over lambda L, we can ignore this term, and we conclude that lambda L is less than or equal to 2 pi over beta. Yes, Sasha.
In your argument, this was an analytic function inside the strip went to infinity, right? But probably you want to cut it off, and so you're saying that it will not affect any argument. And how would you bound the function of this?
That's
force?
right. So the complex analysis result, the Schwarz-Pick analysis theorem, is about a mapping of unit disks to unit disks.
Right.
So here we're mapping this strip to the unit disk using a conformal transformation.
Yeah.
You can map, we're mapping an infinite strip to the unit disk.
Yeah.
You can cut off this strip somewhere very far over here. It won't affect the conformal transformation in the region that we're interested in it.
But how you bound the function as this edge?
Good. So, good. All we need is to find a time which is much shorter than the recurrence time, such that the magnitude of the function here is less than fd.
Okay.
And this is a function, this is a function that's decreasing. So it spends almost all of its time exponentially small. You can show this by writing down an answer involving phases and averaging it. So the function is almost always very small, and we just need to find some time to cut it off before the recurrence time where it's less than 1. Okay. Yeah, thank you for raising that technical point. Okay, so I'm almost out of time, and I'm almost done. So let me just make one more comment, which is that, right, so in this case, we had to rely on this assumption that this factorization of this 4-point function with this ordering was true at large T, up to uniformly small errors. There's a setting where we consider this a special case of a thermal quantum system, which is given by a system in Rindler space, where let's say we consider a conformal field theory in Rindler space at finite temperature. We can relate these 4-point functions to 4-point functions in the vacuum. Right? The Rindler space is the Rindler thermal system on Rindler space is equivalent to the global vacuum. And then it's possible to prove this statement using the operator product expansion on the global vacuum. So for the case of a field theory in Rindler space, we actually have a mathematically rigorous argument. In the more general case, we have to rely on this factorization assumption that as we make this time large, that the 4-point function should approach the disconnected answer. This means that if we consider in ADS a case, we do the Rindler ADS construction here, and we consider this quantity capital F. This is like a high-energy scattering problem in global ADS where we have a W operator here, a W operator here, a V operator here, and a V operator here. This would be F of T plus I beta over 4 in the special case of a system on Rindler space. And so now we get from this result a rigorous bound on the growth with energy of the tree-level scattering amplitude. The reason I like this is because this work of Kamanto, Edelstein, Maldacen, and Zhibotov, where they were arguing for this a similar bound, was very helpful for us in motivating the idea that there could be a bound on this 4-point function. And here we have sort of another argument. I think it's actually a rigorous argument that bound is correct. Okay, I'm going to stop there. Thank you very much.
One question, from the point of view of the bulk gravity, sort of what lessons am I learning from this? It's telling me something interesting about the chaotic behavior on the boundary or in the dual theory, but what can I really learn in the bulk gravity theory?
Right. So one of the slightly frustrating things about this 4-point function is it doesn't seem to be sensitive to extremely high energy physics in the scattering amplitude. There might be some very small tails in this 4-point function that are sensitive to that. But the main thing it's sensitive to is this sort of tree-level iconalized exchange. And so there the thing that you learn is that stringy corrections, for example, can't make the amplitude grow faster than the gravity amplitude would. This was part of the lesson, one of the lessons of this paper I referred to by Kamano, Edelstein, Medelstein, and Zhibotov. And here we have another argument that should be true.
Okay, so it fits with that. Do I learn anything else sort of beyond that, or that's the sort of the main new thing or sort of thing I'm learning about bulk gravity? Other questions? Well, many.
Yeah, Gary.
So I mean, maybe somewhat related to what Steve was just asking. I mean, when Kitaev gave his talk, he also had this 2 pi over beta and pointed out that's the surface gravity of the black hole and the bulk. So in your case, is it connected directly with the surface gravity?
Well, it's the surface gravity. I always forget the exact definition. But what this 2 pi over beta is, it's the relation between Schwarzschild time and the boost of the near horizon region. The boost parameter of the near horizon region is 2 pi over beta times the change in Schwarzschild time. And I think that's the same as the definition of the surface gravity.
Yeah.
Yeah, she.
I have 2 questions. One is more technical. The inequality that you wrote down over there could be violated at small time. So it does.
Sorry, which inequality? We have several inequalities.
The second one.
This one?
Yeah. Because it depends on the coefficient of the last term.
Oh.
That's the coefficient.
No, so this would only make it more true, right? So it wouldn't be that it would be violated. Yeah.
No, I meant the coefficient if it's negative. Then do you know it's positive?
Let's see. So we cannot say for sure that there's a negative coefficient here would make our bound stronger. And we don't have that. We're able to show that this inequality shows up to a correction which might be present of order 1 over n squared. That bounds the behavior of this function once it exceeds 1 over n squared.
Let me think about that.
Tom, you were...
Yeah, I just wondered, below the Hawking-Page transition, there's, in the kind of calculation you're doing, there's no sign of chaos. But that's also a thermal system. So is that just because we're doing leading order large n? We're not seeing the interactions in that thermal system?
Well, I guess it's a thermal system which is sort of operating in the integrable region of the Yang-Mills theory, right?
Yeah.
So
and that's what I'm guessing, that it's a large n artifact.
Yeah.
So those things are approximately not interacting at large n. I'm asking, I'm not,
Yeah, you could ask if you take that system at very low temperature and go to extremely late time, whether there might still be some decrease in the 4-point function. And I'm not sure. But certainly this exponential growth with an order 1 coefficient of the exponential will not be present. Alexei, you were...
Yeah, I wanted to ask about this formula. You said there are 1 over n squared corrections, but we have good intuition for short times. What if at very long times there are bigger corrections?
For which formula?
This trace.
This should be less than or equal to this plus 1 over n squared?
Yeah.
Right. So in the case of... let me give 2 answers to that. First, in the case of the system on Rindler space, one can prove that this is true at large time. At large times, it only becomes, this converges to this plus terms that are exponentially decreasing in time. So that in that case, right, good. But I guess for times, here we're interested in times, we're looking at this type of correlation function, and we're interested in times that are very short compared to the recurrence time. We're interested in times that are of order logarithm of n squared rather than recurrence times, which would be like e to the n squared. And here, I guess that the factorization should really only be getting better as the time is increasing.
It seems like,
It's like somehow the influence on the WW correlation function from the fact that you inserted some V's here they're extremely far apart. So the influence on the correlation function is becoming smaller and smaller. That should be true. I mean, the fact that becomes small as t becomes large should be true in more general systems, and not only in large n systems.
It's the idea that the system thermalizes, right?
Yeah, it's roughly the idea the system thermalizes. Yeah. Sasha had his hand up.
Sorry, what if you take time to be large, but you also separate them in space such that they're light like separated? Wouldn't you expect that the correlator is still large?
Right. So in the case of 2 dimensions, that's true. Well, good. So in this case, we imagine that we smear the operators a little bit in time. So the null singularity is not really a singularity, so it's smeared out a little bit. And there, in 2 dimensions, it's true that the strength of this effect at the light cone doesn't decrease with distance along the light cone. But in higher dimensions, it does.
Okay, so okay.
So in 2 dimensions, we would have to, right, so the large n, it should be true for large n systems, even in 2 dimensions, but for systems that don't have large n, where we're using the large spatial separation as an important parameter, it's important that we work in higher than 2 dimensions. Don?
So, as you remarked, the lambda there is really set by the surface gravity in the gravitational context, and that was why it was insensitive to higher derivative corrections and so forth. But you had this interesting result that in string theory, something was changed. You no longer were growing exponentially the same. I've actually forgotten what it was, but the power of s changed.
Mm-hmm.
Is there some interpretation of that in terms of what's happening to the black hole horizon in string theory, or a deviation from what you would expect? What is the fact that it's no longer growing like the exponential shift you expect from the geometry mean?
So let me explain that. The relation with the surface gravity is all to say that the Mandelstam S parameter is like e to the 2 pi over beta times t.
Right.
Now in gravity, there's 2 facts that make the gravitational answer proportional to this. One is this relationship. The other is the fact that delta is proportional to s in gravity.
Okay.
So in string theory, that's not true. If we, for the moment, consider flat space high energy scattering in Reggie kinematics, what you find there, delta, flat space, string theory, you have s to the 1 minus alpha prime, I think it's over 2 times k squared, where this is the momentum transfer. The thing that happens in the ADS black hole is because of the curvature, even at 0 momentum transfer, we have a non-zero, right, so there's a term like this, which is just proportional to L string, to 1 over L ADS squared, even at 0 momentum transfer. So the growth is strictly less than gravity.
Usually in the spin model, there's this interesting spread of operators. The simple operators become like sums of products of operators. So are there any holographic systems? I'm completely so where you can see this explicitly, you can calculate local operators becoming more and more non-local.
Yeah, right. So this was analyzed in a paper with Dan Roberts and Lenny Susskind using these 4-point functions. And there, what we do, what's important is this function f of b that I wrote. So one finds that the commutator of the operators is like the 1 over n squared times the same factor, 2 pi over beta times t, times a function of the separation x minus y, where this function is exponentially decreasing in space. So we have e to 2 pi over beta t minus mu times x minus y. So this is roughly the thermal expectation value of the commutator of v at x and 0 with w at y and t. Okay. So what this tells us is that when this commutator is of order 1, that defines the radius that the operator has grown out to. The operator has become space-filling up to that radius. So from this one finds that the radius is expanding with time, like what? It's 2 pi over beta times mu. This defines the velocity at which this operator is growing.
I was thinking more like explicit calculation where you have some space of all operators and you can write down Heisenberg equations of motion, but not like expectation value, but the operator equation, expanding some simple operator into sum of all operators.
Oh, no.
That kind of.
I don't know how to do that in holography, no. So there, I mean,
that would be independent of the temperature.
Right. Yeah, it's not about temperature, just the Heisenberg equation of motion. So I don't know, sounds too hard.
Yeah, that's sort of the question that holography isn't very useful at answering.
Okay, God. Well, so let's take one more and that'll be great.
Can you say something about the finite n case? How to prove the bound?
How to prove the bound in...
Or how to derive the bound, yeah.
Finite n? Oh, you mean without using large n?
Yes.
Yeah, so there what we do, what we need... Good. So there it's not true that for order 1 times, this correlation function here is approximately equal to the factorized answer. So instead what we do is we take this strip, here was t equals 0, and let's say at very late time of order log n squared, the function starts to decrease. So what we do is we begin the argument at some intermediate time, t naught, which is chosen large compared to beta, but small compared to log, not log n squared. This would be, the small parameter here would be the distance between the operators we're considering. So the commutator is small until a time of order the distance between the operators. So here we would have a very large time of order the distance between the operators, and we choose a t naught, which is large compared to beta, but small compared to that distance. And then we make the physical assumption that this 4-point function should approximately factorize, not because of large n, but just because the w operators are close to each other, the v operators are close to each other, and they're both very, very far from each other in time. Again, this is an assumption in the general case, but for this case of Rindler space, one can show that it's true based on the OPE in higher than 2 dimensions.
What happens in 2 dimensions?
In 2 dimensions, there are non-decaying. I mean, in 2 dimensions, this is not true. This factorization is not true for times of order, for times near the light cone. So for this, we need the factorization to hold for all times sort of between t0 and this large time x. And in 2 dimensions, then there's a failure of factorization at a time of order x.
So the bound doesn't hold in 2 dimensions for these systems?
So the bound doesn't hold in 2 dimensions for systems without large n. Or at least I don't know how to prove a bound for 2-dimensional systems without large n.
Okay, well, we should give people a chance to go, although this could continue informally. Don't forget the dinner organization right after this. So thank you, Don.